Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 1950 marked a significant milestone in our understanding of the fundamental building blocks of matter. Cecil Frank Powell's work, titled Photographic Evidence of the Existence of New Heavy Mesons, stands as a pivotal contribution to the field of particle physics, a field then nascent but already brimming with promise. To appreciate the magnitude of Powell's feat, it is essential to understand the intellectual context from which it arose, the scientific climate that nurtured its development. Prior to Powell's contribution, the landscape of particle physics was undergoing a period of rapid transformation. The discovery of the positron by Carl Anderson in 1932 shattered the prevailing notion of the electron as the sole constituent of negative charge. This, in turn, was soon followed by the conceptualization of the neutron, a particle possessing a mass comparable to the proton but possessing no electrical charge. The atomic nucleus, once considered a simple entity, rapidly evolved into a complex aggregate of protons and neutrons. These discoveries, however, raised fundamental questions about the forces binding these particles together. The prevailing theory, championed by Hayakawa, predicted the existence of a particle, a mediator of the strong nuclear force, with a mass intermediate between the electron and the proton. This hypothetical particle, the meson, became a central focus of experimental physics. Powell, by this time, had already established himself as a prominent figure in the field of nuclear physics. His earlier work on photographic emulsion techniques proved to be revolutionary. Instead of relying upon the more complex and less efficient Wilson cloud chambers, Powell refined the method of studying particle interactions by observing the tracks they leave in a photographic emulsion. This emulsion, prepared with high concentrations of silver bromide, served as a highly sensitive detector. When a charged particle traverses the emulsion, it ionizes the silver bromide grains along its path, leaving a trail of developed silver atoms after processing. By meticulously analyzing these tracks under a high-powered microscope, Powell and his collaborators could measure the particle's charge, mass, and energy. This innovative method provided a new level of precision and facilitated detailed studies of particle interactions. The essence of Powell's 1950 paper resides in its meticulous application of these emulsion techniques to the study of cosmic rays. Cosmic rays, energetic particles of extraterrestrial origin, bombard the Earth's atmosphere, producing a cascade of secondary particles, among which the then elusive mesons played a crucial role. Powell's team, stationed at high-altitude sites, such as the Pic du Midi in the Pyrenees, exposed photographic emulsions to the flux of these cosmic rays. Their analysis led to the identification of several new and previously unknown mesons, a feat of experimental ingenuity. These mesons exhibited unique properties, differing from the pi mesons or pions, which had already been discovered. The charged pi meson, already known to decay into a muon and a neutrino, had been observed. The team subsequently documented the existence of a variety of heavier, unstable particles. Powell's team, through their detailed analysis of the emulsion tracks, determined the mass, charge, and decay modes of these new particles. The mechanics of Powell's approach involved incredibly detailed observation. The tracks left by these particles, curving due to their interaction with the magnetic field, were analyzed using precise measurements of range, scattering, and ionization density. The curvature radius, the ionization density, and the length of each track were carefully measured at multiple points to determine the particles' momentum and energy and to distinguish them from one another. The identification of new particles involved statistical analysis of the parameters deduced from the behavior of the tracks, a delicate procedure that had to account for the errors inherent in the measurements. These painstaking efforts provided compelling evidence for the existence of a new class of particles, with masses significantly larger than that of the muon. These particles, which they termed V-particles due to their characteristic V-shaped decay modes, were the precursors of what we now call the strange particles, including the kaons and hyperions. The immediate impact of Powell's work was substantial. It provided the first experimental confirmation of Yukawa's proposal regarding the existence of intermediate mass particles. Although the specific mesons discovered were not the exact particles Yukawa had envisioned, their identification reinforced the validity of his general theoretical framework. Powell's observations validated the central role of the meson in mediating a strong force. His findings offered insights into the weak interaction, a force much weaker than the strong force, responsible for radioactive decay. The discovery of these new particles helped pave the way for the development of the standard model of particle physics, offering a glimpse into the richer, more complex structure of matter. Powell's work, in addition to its direct impact on particle physics, had profound ramifications for the development of experimental techniques and theoretical understanding. The meticulous methodology employed by Powell and his collaborators set a new standard of precision in the field. Their careful analysis of particle tracks, their statistical rigor, and the sheer number of observations became paradigmatic. Their approach offered a new way to analyze particle interactions with high levels of precision. The widespread adoption of emulsion techniques provided physicists across the globe with a powerful instrument for studying subatomic particles. The work of Powell's team, immediately after its publication, became a subject of intense study and scrutiny. The photographic emulsion technique was quickly adopted and modified by other research groups, leading to further discoveries. The initial findings were validated by subsequent experiments performed at other locations and using other detectors, confirming the existence of the heavy mesons and solidifying their importance to the field. The techniques also led to the rapid discovery of new particles and opened opportunities to study the processes that govern particle. The subsequent evolution of Powell's foundational work is an undeniable aspect of its legacy. The particles discovered by Powell, far from being isolated curiosities, became cornerstones for the developing standard model of particle physics. Their existence prompted new theoretical insights and contributed substantially to a more complete understanding of the constituents of the universe. The study of particle properties, such as mass, charge, spin, and decay modes became critical to the development of models that accurately described the behavior of subatomic particles. Powell's choice of the photographic emulsion technique, while groundbreaking at the time, possessed inherent limitations. The analysis of emulsion tracks was labor-intensive and required highly trained personnel. The particle interactions were difficult to interpret without access to the full three-dimensional information required to accurately analyze the track. As subsequent discoveries were made and as the number of particles grew, the need for more sophisticated and powerful detection methods became more obvious. This eventually led to the development of advanced detection technologies, such as bubble chambers and electronic detectors. This would supplant photographic emulsions as the primary method of observing particle interactions. Despite these advancements, the contributions to the field made by Powell and his group remain of utmost importance. The reception of Powell's work by the scientific community, upon its release, was overwhelmingly positive. His work was celebrated as a seminal achievement that contributed a great deal to the ongoing scientific endeavor. Powell's discovery earned him the Nobel Prize in Physics in 1950, a testament to the transformative nature of his contributions. The Nobel Prize directly acknowledged the profound impact of his work on the understanding of the fundamental constituents of matter. It was also a recognition of the importance of his innovative experimental methods. His discoveries provided an impetus for further investigation and experimentation. Many individuals and prior works influenced Powell's trajectory, shaping his approach to scientific inquiry and particle physics. The work of Patrick Blackett, with his cloud chamber experiments, which had been used to study cosmic rays, heavily influenced Powell's methodology. Powell directly encountered and was significantly influenced by Giuseppe Occhialini, who collaborated on the development of novel emulsion techniques. The theoretical framework provided by Heike Yukawa concerning the existence of mesons was a crucial inspiration for Powell's research. The work of Enrico Fermi, who contributed significantly to the development of nuclear and particle physics generally, also served as a guiding star. The influence of Powell's work extended far beyond the immediate discovery of the new heavy mesons. His work directly impacted the development of particle physics by providing a compelling confirmation of established theories. His methods advanced the field's experimental practices, leading to improvements in future studies. The study of particle properties also advanced, refining the techniques and frameworks for analyzing subatomic particles. The legacy of Cecil Frank Powell and his paper, Photographic Evidence of the Existence of New Heavy Mesons, extends to the present day. His meticulous methods, combined with his sharp insight, opened up a new era in particle physics. His discoveries are an essential component of our modern-day understanding of the forces that shape the universe. His work continues to inspire physicists. It is a reminder of the power of careful observation, rigorous analysis, and a willingness to challenge existing paradigms. His work, therefore, speaks to the essence of scientific inquiry. His observations, innovations, and discoveries are testaments to the power of human intellect.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.